I'm pretty sure it was only a few hundred feet above the ground.
When I first moved to Albuquerque, I lived in a house, running a house that was just near the medical school up here north of campus. And I woke up and I heard, and a balloon landed in my backyard.
Wow. Your backyard?
Yeah.
Did you get a picture?
Yes, it was crazy. It was totally
That's
crazy.
really cool.
I was like the Wizard of Oz. I expected the wizard to just like jump out of there.
The truck with all the people come knocking the door and go, here we got a balloon. So, yeah.
It was insane.
Emergency landing.
All right, fearless ones. So, we will have a problem session this afternoon to talk about the next assignment. So, all right, so what we talked about yesterday, and we'll continue to talk about, is spontaneous parametric down conversion. And entangled light. So when we talk about, as we were discussing yesterday, when we talk about entanglement, we have to think about entanglement with respect to whatever the subsystems are, whatever the degrees of freedom are that are defining our subsystems, okay? And when we're talking about light, we have different ways of thinking about the degrees of freedom. We can think about the particles, the photons. The photons have, you might say, 4 degrees of freedom. What are those 4 degrees of freedom? There's motion in 3D. So the momentum could be this way, or that way, or that way. Those are 3 degrees of freedom of the photon. And the other one is its polarization, or its spin of the photon. Those are all degrees of freedom that we can think about entanglement. Yeah?
We're not talking about energy.
Well, the energy, of course, is a function of the motion, right? So if I have a certain momentum, I have a certain, the energy and momentum are just related through E equals P times C for a momentum for a photon. So these are the possible degrees of freedom, but we can also think about the waves. And the waves have quadratures, X and P. So that is a degree of freedom. That is a property not of any one quantum of light, but about the collective state of the field, which is not a particle degree of freedom, we might call it a wave degree of freedom. And amazingly, this process of spontaneous parametric down conversion creates entanglement in all of these different ways, okay? We'll talk about that today. Interesting. What is the situation? So what we're talking about here in spontaneous parametric down conversion is a situation in which we have typically the strongest is that we have 3-way mixing. We have a Chi2 crystal of some kind, and we pump it with some high frequency laser. It's near, 400 nanometer type laser, 400 to between 300 and 400 nanometer laser, okay? And what can happen in this situation is what we get parametric fluorescence. Parametric fluorescence is a process by which one of these pump photons spontaneously decays into a pair of daughter photons that conserve momentum and energy to the degree to which this crystal is very long and the momentum is very well defined, okay? Because there's an inverse between where localized things and we have a momentum uncertainty. But to the degree to which this is a very long crystal, momentum and energy are conserved, and we can get a situation whereby we get, you know, a I just got this pen from the office and already it's dead. We have one photon which we might call the signal, and another photon which we might call the idler, which can be emitted in this process. That's called parametric fluorescence, or parametric down conversion. It's called down conversion because we down converted from a high frequency to a low frequency, because we must have the situation whereby energy is conserved, the pump frequency is equal to the sum of the signal and idler frequencies. And at the same time, we have to have momentum conservation, which we call phase matching. As you may remember when we talked about this some weeks ago, which tells us that the pump wave vector has to equal the sum of these. So we have the situation whereby we have, say, the pump, let's call that the z direction, and then I had the situation whereby I had a signal photon with this wave number. Doesn't work. So yes. And the signal. And now, as we discussed in this situation, there's more than one way. In fact, there's an infinite number of ways in which we can satisfy this phase matching condition. Let's be fancy, and let's make this color. We can have another situation whereby, for example, we have a degenerate, for example, this might be, so this is, I'm sorry, this is the signal, this was the idler, this is the signal, and this is the degenerate. So there's another possibility here where I have something which goes like this or like this. And a whole rainbow of such possible cases that can satisfy the phase matching. Yes, Omar?
So here my input beam is only pump.
That's right.
Okay, so as long as my momentum and energy is here conserved.
Then this is any of those are possible. Okay. And now the phase matching condition and the angular distribution of this fluorescence depends on the simultaneous satisfying of these equations. We remember that the magnitude of the wave vector is omega over c times the index of refraction associated with that particular field. And we have to satisfy this for both, we can break this up into a component, a parallel component, and a perpendicular component of the field. So as we see here, the perpendicular components have to be anti-correlated. They have to add to 0 if relative to z, and then the longitudinal components are whatever they are. But in order to satisfy this equation, we cannot do this. We can't satisfy this equation if the pump and probe fields all have the same functional form of the index of refraction. There's no solution to that equation. We can have that if the index of refraction as a function of omega is different for the different fields. And that can be true if the polarization, I'm sorry, if the index of refraction is a function of the polarization, okay? So we can arrange it such that if we set up, let's say, I can't draw perspective right, let's say the polarization of the pump is out of the board, then or actually I'll do it the other way, let's say it's like this, so the polarization of the pump, then we can have a situation where all of these guys have the polarization perpendicular to it, and these photons are emitted in this way with this polarization because they satisfy this equation, okay? And when the two photons have the same polarization and we've arranged the crystal in such a way that the index of refraction for the different polarizations satisfies this equations, when both the signal and Idler have the same polarization, we call that type 1 phase matching. Okay. So we can think about this in a kind of level diagram whereby, you know, there's a ground state of the crystal and we're pumping it, and we can have different situations whereby we have fluorescence like this, or we have fluorescence that looks like this, etc., etc. All of those are possible fluorescence. Now, I just mentioned one small fact here. You may remember the point about parity. That is to say, if I start with some initial state and I excite towards an excited state, and this is an electric dipole transition, the excited state should, if this has a definite parity, this has to have the opposite parity, okay? Because the dipole operator is odd under parity, so if I start with an even parity, I have to get to an odd parity state. But the two photon transitions would be one that maintain the parity. So these cannot be eigenstates of parity. We can't have a material that is mirror inversion symmetric. It has to have a direction of stress or strain. And so, for example, in an atomic gas, we can't have three-wave mixing because the atomic gas, the levels have a definite parity. And so the crystals that we use to do three-wave mixing of this sort are ones that have a stress or strain, which is why they have this birefringence and the index of refraction different for the different polarizations. If you want to do this kind of parametric fluorescence in atomic gas, you have to do four-wave mixing, where you absorb two photons and you emit two photons, and that's done in Elaine Becerra's lab, for example. Yes, Ben?
Is that quality in the crystal that you just described, is that a consequence of nonlinearity, or is that in
No.
addition to nonlinearity?
No, it's an addition. The nonlinearity, I mean, atomic gases have nonlinear response, but they're not, but they're parity symmetric. The parity, the breaking of parity is related to the fact that the crystal reacts differently if you push it this way than that way. And that's just about the crystal structure. It's the fact that it's in a crystal. Yes, Omar.
What if we apply a very large electric field to induce sparking?
And if we don't have parity as a good, if we can have states that have mixed parity, then yes, we can absolutely do that. We can do that, absolutely. But we have to break parity symmetry in some way. All right, cool. So what we discussed, I missed my chalk. These stupid things and pens and, all right. So this whole picture is rotationally symmetric, right? I can take this thing because this beam is, everything is cylindrically symmetric. So actually, this thing is emitted in a cone, okay? So you have a cone of light and these different cones. In fact, the parametric fluorescence is the picture of every quantum optics textbook, right? This one is by Garrison and Chow. These were my two PhD advisors. Actually, you can find my PhD thesis in this book.
Wait, actually?
Yeah, well, parts of it. The thing I worked on, John Garrison. Anyway, so, but you know, this is one thing to remember. This is actually backwards. This is an artist's rendition. The photons that come out of this are typically infrared. They're not this color because they're half the frequency of this. It has double the wavelength, so they're typically 800 nanometer-ish wavelength. So this is an artist's rendition. The higher frequencies are actually the inner cone, and the lower frequencies are the outer cone in order to satisfy phase matching. That's why I got confused yesterday. So what comes out of this situation is a situation where we have cones of light that look like this. They're all polarized in the same direction in this type 1 phase matching, okay? They have the opposite polarization to the pump, but equal polarizations to one another. That's called type 1 phase matching. And because of this correlation, the momenta, the transverse components have to cancel, as we just said. The light, these correlated photons come out on opposite sides of the cone. So I could have a photon here emitted, and then its conjugate would be this one. Damn you. Okay, from now on, purple is green. Imagine it to be green, okay? Or I could have a situation, I'll draw this picture, where a photon is here, it's this, I'll call it this guy, just give it, and then its conjugate one is this. And all of the above, all possible photons that satisfy this, that their frequencies add up this way and the momentum, but they always come out on opposite sides of the cone because of this momentum conservation, as we said. Now, formally speaking, as we discussed yesterday, we can think about this in terms of the Hamiltonian that describes the three-wave mixing process. The Hamiltonian that describes the three-wave mixing process is an integral over the crystal size. And then we have some constants here that depend on chi2 and other things, a process by which we annihilate the pump photon in its wave vector and create a photon in the signal mode and create another photon in the integrated over all of these modes, okay? So the Hamiltonian, the three-wave mixing process involves this, plus the Hermitian conjugate, whereby I annihilate one of the pump photons and create the pair, where this thing is e to the I k pump minus k signal plus k Eigler dot r. And then in the Heisenberg picture, we have omega p minus omega s plus omega I t. All that is in there, okay? In the limit that this is a strong pump, whereby we ignore any effect of the depletion of the pump, we replace this with the amplitude of the classical amplitude of the pump, and we have a process whereby we have creation of pairs of photons or annihilation of photons. And this is what we saw was the squeezing Hamiltonian when we were studying how squeezing was created. But if we look at this in this perturbative way, if I think about the time evolution operator of the system, the scattering operator, acting on the vacuum, if this is a weak interaction, if chi2 is small, then we can look at this to first order perturbation. And this thing is approximately equal to the vacuum minus I over h bar times this time ordered thing. Well, now I don't have to time order it because I just have one guy minus to infinity dt prime, h of t prime acting on the vacuum. Okay. So that's just the first order expansion if this is weak, which it generally is. Okay. And so if we look at it in this order, the state that comes out is a superposition of the mostly vacuum and a little bit of this acting on the vacuum, which is a 2-photon state.
So you're saying that if the pump is weak, it can do that?
That's correct. And chi2 is sufficiently small, right? Yes?
S and L are what, the two idlers?
Where's L?
K.
K sub I.
Oh, excuse me.
Signal and either, pardon me. Yeah, minor.
What is the pump weak compared to?
The pump isn't weak.
Okay.
It's the product of chi times this that has to be a small energy.
Okay, so chi2 just needs to be sufficiently smaller than E.
Not that EB, but the whole constant together with all the other constants are such that this is a small energy. What it physically means is that most of the time, this pump photon just goes through this crystal and does nothing. But every once in a while, this happens, and it happens rarely. The rate at which it happens depends on chi2. Good. So this state is a 2-photon state. Okay. And when all is said and done, when we apply this and do all these integrals, this 2-photon state is equal to the integral over all the momenta of the photons times some amplitude that depends on these two guys, and then the creation of the signal and either photons acting on the vacuum. Okay. So this state is an entangled state. In this case, it's entangled in the motion of the photons. This is the 2-photon wave function. 2-photon momentum space wave function. And the nature of that 2-photon wave function depends on the geometry of the crystal and all these integrals, okay? Now, I just want to again re-emphasize here, my Hamiltonian is a sum or integral over these modes of many different, if you want to call them, 2 local terms. They involve the interaction between the signal and either. And because it is a sum or integral over all those sums, we have a superposition of all these 2 possibilities, which makes this generally an entangled state. So, in its simplest approximation, this two-photon wave function has the following form. It's just a delta function in the energy of the photons and a delta function in the momentum this way. Okay? This is the case that we would have if we have perfect phase matching. You remember we discussed phase matching some weeks ago. This phase matching condition is coming from the integral. There are two integrals here. There's the integral over time, which is if this is a scattering process, will conserve energy. This becomes a delta function. This thing is a delta function only when the crystal is long enough and wide enough that when I integrate over all space, this thing becomes a delta function, okay? So in that case, this is the two-photon wave function. It's the two-photon momentum space wave function. And this function is not separable in terms of a wave function for one photon and the wave function of the other. It's correlated. They have spatio-temporal correlations, and thus it's entangled in momentum. It's also entangled in energy because the energy is related to the size of the momentum, right? The magnitude of the momentum determines that. So this thing is entangled in all those degrees of freedom, those 3 degrees of freedom, okay? Now, because of this way, this phase matching condition, I can pick out, if I choose to, two conjugate beams. So I could imagine putting, for example, a pinhole which lets through, oh, I guess I just erased it, but let me draw it again. So, here's my crystal, and I send in this pump, and I put a pinhole here which only lets through this direction, which is reddish. I mean, there's a spread depending on the size of the pinhole. And then we know automatically that there is a conjugate direction over here which will be emitted, which is the green guy, okay? So I can think about two beams of light that are propagating in some major direction. We would call that a paraaxial direction, as a most direction. So we've picked out some transverse component of the beam, and that is correlated with that color through the spatio-temporal correlations, okay? But I have a spread of frequencies. This pinhole is not 0, and that spread can be relatively large, so they have a pretty big spread in frequencies, okay? In that case, I can think about my two-photon wave function in that case as being associated with all the pumps and signal that are within this pinhole where I've picked out certain directions, but some spread of frequencies. In which case, we often write the two-photon wave function for that situation where I have picked out these two conjugate pairs and created that beam as being energy correlated. We've picked out already its direction, but its energies are correlated in this way, okay? So I want to think about this for a moment. This kind of state is in fact just like the EPR state that we talked about in the EPR paradox. If we think about the frequency as the magnitude of the wave number, then in that direction, that is like saying the total momentum, the momentum of this plus this, the center of mass momentum, if you like, along the direction of propagation is fixed. It has a definite center of mass momentum. It has along the direction of propagation. That's what we call the longitudinal direction. But its relative momentum is completely uncertain. But if its relative momentum is completely uncertain, its relative position is definite. Now, position in this case is often called time, because we think about, if we think about two photons traveling, let's just think about two photons traveling along the same direction, the z direction over here, and they're traveling near the speed of light. Maybe there's an index of refraction. They're separated by some distance, but they will arrive at my detector at two different times. So typically, when we're thinking about the correlations of photons along the direction of propagation, we call those temporal modes, because we're typically measuring them not along different positions along z, because they're moving at the speed of light. We stay here with our fixed detector and we see when the photons hit them. So we call those temporal correlations, okay? But they are, of course, through the retarded time, spatial correlations along the direction of propagation, okay? And so if we Fourier transform this into the time domain, then we get the following. So, to the degree to which we can think about this as effectively infinite bandwidth, of course not. Really, I should have some function here that depends on how big the pinhole is. And this guy would then be some function, some narrow function of that's the inverse Fourier transform. Let's call this A tilde, and that's A. This is the Fourier transform of that. If this is flat, this is a delta function. But the main point I want to emphasize here is this spatiotemporal correlation. When these two photons are emitted, according to this kind, to the degree to which I idealize it in these delta function forms, what it's saying is that the two photons are emitted at the same time. That is to say, Ts is equal to Ti. They are actually on top of one another here. But their center of mass position, as to say, when they are emitted, is uncertain.
Sorry, so I think I'm confused. So when you're talking about the spatial temporal photon, you're talking about two photons in the same conjugate modes, right?
The two photons in these conjugate modes, these two photons, and I'm asking about
Okay.
where they are along the direction of propagation. So their relative position
Okay.
and their center of mass position.
So, okay, so
Along the
those two
direction of
photons
propagation.
are your, what photon is in what? What are those modes?
That's right. This guy I'm calling the signal,
Okay.
and this guy I'm calling the ether.
So what you're saying makes sense and follows from the map, but I'm trying to reconcile it with what we can actually measure. And what's stopping me from just noting the time I get a click on the photon detector and then back calculating, oh, we know it's going at the speed of light?
Right. Well, the question is, you'll get something, but if you measure it, will you get the same thing the next time you measure?
Oh, I see.
So there's an uncertainty. You measure something. So we have a wave function which tells me the probability amplitude of detecting a photon here and a photon there. And this is the two photon wave function.
So in the distribution, there's a wideness.
That's correct.
Yeah, I see.
So the photon that is, the point here is that to the degree to which this is not a pulse, this is what we call a CW, or continuous wave, or monochromatic field, we have no idea where the pump is. The pumps to the degree to which I treat this as a plane wave, the pump has a definite momentum. It has an absolutely uncertain position. We don't know where the photon is. So we don't know when the photon is going to hit this. But when it hits, the two photons come out together. Okay? So that's another way of saying is the photons are twins. They're born simultaneously, but their birthday is completely uncertain. We know they're twins, but we don't know when they were born. Yeah.
So the uncertainty actually comes from omega p itself, or kp.
That's right.
Because initially it's not a plane wave, it's a small packet with a
No. This guy is a plane wave.
approximately.
Yeah, but if it wasn't, this wouldn't be a delta function.
Yeah, but end of the day we are adding another convolution, where it's,
This guy?
yeah.
That's coming from the fact that I have a pinhole.
Oh.
See, the pinhole, the size of if the pinhole was a set of measure 0, I would not have a spread in frequencies. I would have a definite frequency. Because the frequency and direction are correlated through this. I need to have a spread of frequencies in order to have that. Yeah.
So, in any instance where you measure how many, where you measure something here, you'll end up measuring that, one photon exists off in this direction and one exists in the other
That's right.
direction. But before you measure it, you have this field, so you
That's
have a
correct.
probability density. Is that kind of, so when you take the pinhole, you're throwing away a bunch of stuff that
Right.
can't be anymore,
Yep.
and now focusing on
You
this.
projected the state onto this subspace.
And is that fact that you're going from this probability density and then cutting out pieces part of what's giving us this packet? So that you make that pinhole measure 0.
That's right. The size, the spread, the size of the packet depends on the size of the pinhole. This function will depend on the spectrum that is met through that pinhole. Okay. So we were talking about last time, and I'm sort of just,
One more thing.
yes, I'm listening.
So imagine, well, we can always imagine, it's always true that we cannot get exactly a plane wave.
Yeah.
So I have some uncertainty there.
Yes.
I'm also doing this pinhole, so how does this affect that?
That will affect this overall two-photon wave function. So this two-photon wave function that I've written down is complete idealization. It's an idealization in two ways. One, that we have a perfect plane wave of the beam. The pump was a plane wave. and secondly, that the crystal was infinite. So that these things became delta functions. If I have, well, it's already erased, but when I had replaced the idler by, when I replaced the annihilation operator for the pump by the amplitude of the pump, really I should be replacing it by a Gaussian beam, which means I have a range of pump vectors that localizes into a beam, which will change these correlations. These won't be perfect delta functions. The other thing that I might do, and people do, is instead of sending in a CW monochromatic beam, to send in a pulse that has, a certain extent in space or duration in time, a femtosecond pulse or something like that, or a picosecond pulse, which would mean that the birthday of the photon is somewhat defined by when the pulse entered, and that would change these correlations as well. But it's worth thinking about the idealized case first.
Okay, so if it's idealized, what does that thing do?
Well, what I'm saying is it picks out a set of Idler or signal photons that can pass through here. They have a spread of possible frequencies. So the shape of that pinhole affects this. But to the degree to which, again, I can idealize that as effectively flat, use this. And this was first measured in the famous Hanlo-Mendel experiment. So in the Hanlo-Mendel experiment, what they did is they took this type Chi2 crystal and they put these pinholes here, whatever they defined it, and then they looked at the coincidence counts, as you may remember. And so what comes out of here are two wave packets that are very, very narrow to the degree to which this is a broad spectrum. And they can then change whether this is a balanced equal time or not, so that if these two photons are identical photons and are incident of the beam splitter, you remember they either both go out this way or they both go out that way, and I'll see zero coincidence, right? And what they measured as a function of delta L was this. So we'll see this situation where I can see no coincidences if this delta L is sufficiently small, that is to say, the path lengths are almost exactly matching, and this looks at the overlap of the two photons, right? So when the two photons overlap, I don't see any coincidences. Otherwise, one of the photons can go here from the signal and the other one can go to either, and I can see a coincidence count in the background. But if this is perfectly balanced, and they were using this to measure the duration of the photon, this was a few nanoseconds. In this. So that they were using this as a way of measuring the relative time by which the two photons were emitted. And they were emitted effectively simultaneously. Okay? Now, they didn't, later the whole Hanlo-Mendel thing became a much more important thing about two-photon interference, but they originally weren't thinking about it that way. They just wanted to measure this quantity, what is the time difference between the emission of these two photons? And they measured it
Does
this
the
way.
signal either have to be degenerate?
No, they don't. They don't. not for this. Right, okay, so, yeah, we talked about other kinds of two-photon interference. I'm not gonna repeat that. Given the time, I'm gonna cheat a little bit, and we're gonna just look at, I wanna tell you just some facts. And, because I wanna, I'm just gonna use my laptop here and the notes to explain some other factoids. All right, let's see. Come on. It worked a moment ago. Jeez, that's good. All right, so there's a few other things maybe I'll just mention. So in addition to the temporal correlations that we just described, where the two photons are emitted two times, I also have these transverse correlations, right? The photon can be emitted this way or that way, which is about its transverse momentum, not the momentum along the direction of propagation. Those two are correlated. Those two are entangled. And that's called spatial mode entanglement. That spatial mode, we talk about temporal modes and spatial modes. The spatial modes are all entangled. And in fact, you can think about that kind of entanglement as entanglement associated with the orbital angular momentum of the photon to the degree to which I have a cylindrically symmetric beam. So that's a whole nother story, but we can have both temporal entanglement and transverse correlations. That's written up here. But what I really want to tell you about in the last number of minutes is about polarization entanglement. The polarization entanglement that is created in the so-called type 2 phase matching, which I'll explain in a moment, is the source that was used in all the violations of Bell's inequalities, okay? They created effectively the Bell state, okay? The Bell state is more easily described in terms of the qubit rather than this continuum, of possible, the continuous variable type entanglement, okay? So in order to do that, you can't have the signal and idler have the same polarization as we described in type 1 phase matching. You need a different kind of phase matching whereby you get momentum and energy conservation for a functional form of the index of refraction that is different if the two photons, that is, say, the signal and idler, have orthogonal polarizations. So you can arrange the crystal in such a way that we satisfy the phase matching conditions. We satisfy that omega p equals omega s plus omega I, and kp equals ks plus ki, when the index of refraction of the two guys are not the same. One is the ordinary wave, one is the extraordinary wave, okay? And it turns out when you do that, you get this emission pattern, okay? That, I won't derive this for you, But what you get is two cones that are offset from one another. You get a cone of light that we can call the signal cone, which is, say, polarized, we'll call it horizontally. And then the conjugate one is emitted not in the same cone, but in a different cone in order to satisfy these conditions, and we'll call that depolarized, okay? And it's the same kind of thing relative to this point. Things on opposite sides are conjugates. So this horizontally polarized photon is correlated with this vertically polarized photon, okay? This vertically polarized photon is correlated with this horizontally polarized photon. Now, let me ask you a question. Suppose I put two pinholes like this, okay? I put one here and one here. Are these going to be polarization entangled? Well, I'm not, the question is the state of the system entangled where one of the photons is, say, horizontal and the other one is vertical, but I don't know which it is. It looks like a Bell state. So if I put a pinhole here and a pinhole here, will these photons be polarization entangled? Yeah.
Are we able to like separate them into differently measurable modes?
Well, they are. I mean, this one comes out here, this one comes out here, and I can, you know, direct one to one detector, one to another detector.
Wouldn't, like, don't you need 2 degrees of freedom to call something entangled? Like, just calling it the polarized entangled, like there's one here, one here.
Well, okay, you're getting there. I mean, if I thought about this in first quantization, I want the state that looks like this, maybe with some phase in between them. I want a state that looks like that, where I have two photons. One of them is horizontal, the other one is vertical, but I don't know which is which.
Do we know which one is, so, okay, do we know that the one going this way is horizontal?
We do.
Already before measuring it?
Yes, because we put a pinhole, and the photons that come out here are horizontal, and the one that comes out
Well,
here is
no.
vertical.
Well, no.
Well, the answer is no. The answer is no. And the reason is that the polarization is correlated with the momentum. And so if we trace out the momentum, we no longer have entanglement in the polarization. We have, because of this pattern, we have correlated the momentum with the polarization, and there's something called the monogamy of entanglement. You know, there's not a polarization sexual revolution yet, but that's the way it goes. So you can only be polarized with 1 degree of freedom, and I mean entangled with 1 degree of freedom. And so because the momentum is in some sense is information about what polarization it is, there is no entanglement between polarization of those two photons. But there is one case of one pair of photons here which are polarization entangled. Which one? The green ones. Because if I look at this photon, it definitely has that momentum, but I don't know whether it was emitted on the horizontal or the vertical cone. And similarly here. So I separated out the correlation. I've made them indistinguishable. And formally speaking, what that means in that case is that I can separate out the momentum space wave function. The momentum space wave function is now producted with the polarization wave function. They both have the same momentum, so it's just a product state of those momentums with that. And that creates a belt state. Okay? So this is what's written over here. Boy, isn't it easy when I don't have to write anything on the board? This is the worst way to teach. This is when I can show you as much, you know, I never absorb anything. But anyway,
It's too easy.
yeah. So you see the point here. This is the case where that one momentum had H, but it also could have had V, because they overlap. And so I can factor it out and get that state. Okay? Now, the problem with this is that you've thrown away a lot of the photons. And it would be much nicer is if you could use them all. And so my good friend and very famous physicist, Paul Kwiat, devised this thing back in 1999, back when we were all still partying. And the idea was the following. Let's think, instead of thinking about that type 2 phase matching, let's imagine two crystals whose optical axes are oriented in such a way with the right birefringence, such that I get type 1 phase matching here for photons coming out with V polarization, and crystal number 2 is also does type 1 phase matching, but if the polarization of the pump is in the orthogonal direction, it will emit H polarization, okay? So there are two cones, one cone of H polarization, one cone of V polarization. And whether I get this or not depends upon whether the pump was polarized like this or polarized like that, okay? But if I put the pump at 45 degrees, there is a superposition of the pump being polarized like this or like that. And if I don't know in which crystal the pump might have been down converted into these fluorescents, then I have a superposition of these two cones. And you can make it where the crystal is thin enough that those two cones overlap, and you get a completely bright source. Yeah?
Using a similar method, could you also have it so that they completely interfere and cancel out?
If I had both, they don't interfere if they're in orthogonal polarizations. If they're in the same polarization, then it's just sort of a larger crystal. So I think the answer is no, but I'd have to think about it harder.
It's not that these cones are like waves that are constructively interfering, right? It's that half of them are here, half of them are here, and if the two halves overlap, then that's all of it, right?
That's right. But I have to think about the probability amplitudes. Anyway, this is just to say that this, you know, also interestingly allows us to create what we call hyper entangled states, where when we have these overlapping crystals, we have basically entanglement in all of the degrees of freedom that I talked about at the beginning. We have entanglement in the polarization. We also have entanglement in time and energy, the time-energy entanglement. And finally, this spatial correlation. All degrees of freedom are entangled in a way that doesn't ruin their entanglement because it factorizes. And it's a very powerful source of thinking about how much information you can pack into all of the different degrees of freedom for multiple entangled modes. This is the most powerful source of non-classical light we have. We're out of time, but you're going to see this. We'll talk about this in the problem session because it's the idea of mode entanglement. That in fact, in addition to the entanglement in the momentum and spin of the photons, the light that comes out of this this parametric fluorescence is in fact entangled in the quadratures. And that entanglement in quadratures is related to the fact that multi-mode squeezed light is entangled. The quadratures are entangled. And we'll talk about that. You have a problem for that in homework, and it's quite closely related to the state that EPR postulated. The state that EPR postulated is in fact a two-mode squeeze state. Yeah.
So the fact that, like in our homework, like a couple months ago,
Yeah.
we found that if you do multimode squeezing, each independent one becomes worse.
Yeah.
Objectively. That's like equivalent to saying
It's the same thing.
if you have a bell state, you trace out one of them, you have a more mixed state than you have.
Correct. All right, very good, folks. We'll call it quits. I'll see you at 1 o'clock. I'll continue to see some of you now.
So squeeze states are necessarily entangled?
Not necessarily.